1, 2, 3, 1, 2, 3. If you are an investor in photonics, you'll recognize where I'm standing. Hello from Frankfurt Messe, which will be the venue for the ECOC Conference 2024. And it's the 50th time that the European Conference on Optical Communications will be organized. Now, you may know that Optica is an official media partner with ECOC. We contribute to their events like the top conference in London, and they help to support our events around the world. And when it comes to the ECOC Conference 2024 in September, we have a lot planned for the more than 6,000 people and 300 companies, many of them Optica corporate members, expected to show up. Optica will contribute to the sessions, we will do the live interviews on the exhibition floor, and we will organize the annual Optica VIP ECOC reception for our corporate members. But it's going to be a little bit different this year, since we are at the financial capital of Europe, and many of our corporate members are looking for investment and investing opportunities. Let me show you the spectacular location we have found. I am at the Osten, next to the main river and in front of the European Central Bank, and this will be the location for the Optica Executive Reception at ECOC 2024 on September 23rd. I am in Montreal, Canada, and behind me is the CHUM Hospital, one of the most important hospitals in this country. This will be the host of the Optica MedTech Industry Summit next 8th of October. Do you know that it takes about 10 years to put photonic innovation into the medical market? Bringing technology to save lives in photonics is the biggest valley of death. How can we solve this? In our opinion, we need to create a forum of discussion between companies developing photonics technology, medical doctors, policymakers, and regulatory institutions. Let's do that at a different hospital every year, and let's start right now. On the 8th and 9th of October, the CHUM Hospital will host companies from all over the world at executive level discussing their photonics technology, the roadmap towards medical trials, and which companies can play a role to help them get there faster. See you in Montreal on the 8th of October. On Tuesday, August 27th at 10 AM EST, we start our new season of online industry meetings. This one is focused on the critical aspects for the future of photonic integrated circuits, manufacturing, packaging, and testing. As usual, our online gathering will be divided into two groups: integrators of the technology, so-called the buyers, and solution providers. This time, we'll hear the demands of GlobalFoundries from Vikas Gupta, Sumitomo Electric Industries from Yasutaka Mitsuno, and the European pilot line PIXAPP from Peter O'Brien. And the list of the enablers will include the leading R&D center imec, represented by Philippe Soussan, the OSAT PHIX, represented by Stefan Heinemann, as well as Simone Cardarelli, MicroAlign, Philippe Dietrich, Keystone Photonics, Laura Horan, Vanguard Automation, Martin Roger, Fintech, Alex Wu, Suruga Seiki, Alexander Harvik, Delo, Gianni Preve, Visio Robotics, and Jörg Smolensky from Nanoscribe. The meeting will address the unique challenges in PIC assembly and test, including number 1, need for precision alignment, number 2, effective thermal management, and number 3, how do you test the final result using electrical and optical probing. And we will discuss the shift towards wafer-level capable processes as well as volume ramping up. And you can also watch live on YouTube later. The meeting is on Tuesday, August 27 at 10 AM EST, at 3 PM in London, at 4 PM here in Malaga, and at any other time in the world, because we are global, we are Optica. I hope all of you went to the beach, had a great summer, and are now looking forward to the start of this industry meeting. We are only 4 weeks away to go back to Malaga, where you saw the video, and meet for the Global Photonics Economic Forum. I think most of you will be there. Thank you very much for the immense support of bringing the industry together. Most of the main leaders of photonics worldwide are going to come to Malaga to discuss the future of our industry. We want this event to continue happening, so I expect to see many of you, I think all of you, in Malaga this year. And now let's start the meeting. This meeting is very important for many reasons. I'm back in Washington, D.C. It's sunny outside, and we have had a really interesting summer. News were coming from companies like Intel. We had this huge thing with Microsoft. Cisco has something to comment on the last weeks. The industry is looking at an impasse. We are now at a moment in which photonic integrated circuits have to develop and have to make it there to be the solution for the next generation semiconductor industries. And for that, we need PICs that can be manufactured, packaged, and tested. And I can tell you the people with me in this meeting room today have the solution. So let's talk together so we can make it all together a reality. And I would like to say that I would like to start the meeting by reminding everyone this meeting is open for everyone to participate. All of you here today with me are participants of an event that is open for everyone. So please, at any time when you have a question, raise your hand and tell us everything that is on your mind. Do not shy away from participating. Let's start, and I would like to tell you also that this meeting is sponsored by 3 companies that are corporate member of Optica, and they have developed fantastic technology. The first one is the one everyone is talking about, all the way from Israel, Newphotonics. They have new technology to advance the speed of silicon photonics, bare silicon modulators at ultra high speed, enabling 200 gig per lane. The second one is OptiWave, the software company providing simulation and design solutions, and they are actually here to help us making better designs and send that better GDS file to foundries. And the last one, last but definitely not least, the European OSAT for the packaging and test of photonic integrated circuits, all the way from Enschede in the Netherlands, PICs. With these sponsors, we built the standard format for the online industry meetings. We received fantastic feedback from this format. We have 2 groups of companies. The first one are the integrators, the adopters. Those companies are going to give presentations of 6 minutes and tell us what they need from us. Today, we have PIXAPP, GlobalFoundries, Sumitomo Electric, and PHIX. And then we have the enablers, those companies who have a solution that could help these integrators with their main challenges. And today, the companies who registered and told us something in advance are MicroAlign, Keystone Photonics, Vanguard Automation, imec, Fintex, Surogaseki, Delo, Visio Robotics, Nanoscribe, Alvis, Newphotonics, and OptiWave. But many more companies registered for this meeting. These are the Optica corporate members that registered for this meeting today. Either they will be live in the Zoom room or following the meeting in YouTube or watching afterwards. If you want to get in touch with any of the participants today, all you have to do is send us an email, and Olga and I will be more than happy to make the introduction. And before I give the floor to the first speaker, I would like to remind everyone that this meeting is live streamed in YouTube. So hello, YouTubers of the world. If you have a question, please write it in the chat and we'll be more than happy to read it into the room. And also, please remind everyone that if you want to find the slides of these presentations, the slides of any other event, or market reports, and we got more than 100 market reports available, go to optica.org/market reports and download everything there. If you're a corporate member, everything there is for free for you. From videos, tutorial, presentation, market intelligence, all of it is there. And last but not least, let me remind that in a couple of weeks, on the 24th of September, our next online industry meeting is on energy. On the 22nd of October, we have a fantastic meeting on virtual reality. 19 November, LiDAR, and we'll finish this season with quantum communication. You can already register in our website at optica.org/industry. Register as soon as possible and tell us as soon as possible if you'd like to contribute with one slide or you have some challenges that the companies can help you with. And with this, I would like to give the floor to the first speaker today. And the first speaker comes all the way from Ireland. For many years, he's been a master of connecting companies and setting up pilot line for the manufacturing, for the packaging, for the test of photonic integrated circuits. He really has been working with me on my previous job and on this one, and it's an honor and a pleasure to give the floor to the director of PIXAPP, coming all the way from Tyndall National Institute, Peter O'Brien. Peter, thank you very much for being with us today. From Washington to Cork, the floor and the attention of everyone is yours.
Thanks, Jose. Thanks for inviting me and the introduction, and thanks to Olga for organizing. So I'll share my screen. Hopefully you can see it. I'll go to full screen. Is that okay?
Perfect.
Perfect. Okay. So as Jose said, I'm director of PIXAPP, the packaging pilot line, the European packaging pilot line. We've been running for a number of years. However, I want to kind of take a step back a little bit, because you may have seen a lot of the services that we provide, but really an important thing is where we're going with new technologies. And historically, a lot of the technologies we've developed are very much package level. So by that I mean the packaging is done in the actual box, or the gold box, or the package itself, and that could be very slow. It's a serial process, and it's not really wafer level. So the move to wafer level photonic and electronic kind of co-packaging is really, really important. And you've probably seen me present this type of organogram kind of chart previously. So looking at the different aspects of optical and electrical and integration, using, for example, hybrid, heterogeneous, and the thermal and the mechanical aspects of all of this. And in one way, it captures everything pretty well. And especially in optics, you see you've got so many choices. It can be very confusing, especially for new entrants into the PIC world, the integrated photonic world, which way you go, which foundry you use, because that really can have big implications on packaging, which takes a large amount of the cost. But what we're definitely seeing, and this is just one example, the actual chips are getting much more complex, very large numbers of optical channels, thousands of electrical channels, and over hundreds. So in this case, it's less than 100. But we do see cases now where we're being asked to look at packaging hundreds of channels. You know, for AI and these types of applications, the optical and the electrical interconnect density is really starting to increase. So things like fiber arrays are becoming prohibitive in packaging solutions. So, and again, in the large volumes that are required, the package level approach, part by part at a time, is really not scalable. So we've been working on a number of projects, and one of them I'll mention here is Photonic Leap. And it's essentially using an interposer. So I'll talk about glass in particular. So essentially where you co-package electrical and photonic devices, for example, silicon photonic devices, on a common interposer platform. And that interposer platform then acts as the base of the package. So for example, you use a ball grid array, as you see here, and have outcoupling. So out-of-plane optical coupling using micro-optics. And micro-optics are becoming very important in terms of enabling pluggable connectors, optical connectors, moving away from bonding the fibers directly onto the photonic chip itself. So it enables 2D arrays and mass scaling, and also, as I say, wafer level kind of parallel processing using more conventional electrical. So I'm limited in time, so I'll just really jump in and show where we are. For example, in this project, Photonic Leap, we work with partners, for example, Fraunhofer IZM Institute in Berlin, where we're developing these glass material. Now, the advantage of glass is it's also being used in electrical worlds, and in this case, we're just using it for electrical packaging. So essentially, we're flipping silicon and indium phosphide devices onto that glass interposer. Now, we're working with fairly small diameter wafers, 200 millimeter, but you can go to very large panels. And here you can see kind of a top-down looking at the vias. So we've got true vias, RF, DC lines. You can create very high density ODL redistribution layers, multi-level, and then flip your devices. And I'll show in a moment how we can achieve that out-of-plane coupling. So again, glass is very good because of its cost. It's a very stable material, and also RF from an RF perspective. And something we want to do in the future is you can embed optical waveguides in glass. So you can use different techniques to embed. So essentially, you can have an optical and an electrical interposer at the same time. And that's really, really exciting. So, in our project, and one of the things we really push in PIXAPP is the development of design rules. So much like a PDK, a process design kit, we want to develop an ADK, assembly design kit. So layout rules And we've been working on that. So developing kind of standardized layout for via size and via dimensions, pitch and so forth, and different types of metallization schemes and gold tin solder for flip chip. Another important aspect, as you've seen in this particular image here, this is flip chip of an indium phosphide chip, out of plane coupling. So, getting that out of plane coupling and having a collimated expanded beam where we can have a pluggable connector, basically like a pluggable electrical connector. We want to do the same in the optical domain. And as you can see, it can be a 2D array. So increasing the actual kind of shoreline density of optical waveguides. So working with Focuslight, who are formerly SUS Micro-Optics, you can see here we developed this out-of-plane microlens array. So essentially what you see here is a cross-section of that microlens. So we've got a micro prism, a turning prism, and that actually is packaged to the edge of the PIC. So essentially just slots to the edge of the PIC and we get that out-of-plane coupling. So that enables this kind of pluggable surface connector. And what you see here then is working with Ficatech, who are also here located at Tyndall, developing automated pickup tools and bonding tools. So I won't spend all the time in this video, but there's quite a number of features here. For example, you see picking up the actual glass interposer. I'll speed through the video. But we've had to modify those machines because, for example, using laser-induced soldering, so coming from the top of the actual package, so I'm modifying the pickup tools, the alignment tools, you can see the ORDL here, and I'll just quickly speed on to the actual soldering process itself. So here you see the actual pickup tool with the window coming from the top. So again, you need to design the tools such that they can be compatible with the flip chip process. And again, working on the actual solder reflow. So here we're bonding the actual PIC onto the glass interposer. So and I won't spend too long here on this particular video, but you can see just towards the end, we need to develop the reflow, and that used an IR camera to monitor and give feedback to the actual chip, so we can reflow the chip and keep that temperature stable. So the message here is designing the equipment hand in hand with the interposers and the chips is really, really important. And the equipment becomes part of that assembly design kit. And here you can see cross-section where we're flipping the PICs and with the EICs, and you see the different multi-level kind of ORDL layers, the vias and so forth, which you can incorporate into those interposers. And very importantly, near the end of my slides here, very importantly, one of the things we've been developing is these what we call reference chips. So essentially these are dummy mechanical, electrical samples and optical samples. They're not functionally active, but they enable us to flip and package devices and look at basic performance, looking at, for example, we've got loopbacks on the optical chip. We have RF loopbacks looking at RF. We have heaters on the chip where we can look at heating. So for example, if you have a power device, you're inducing heating. And again, then we can test and look at, pitch and so forth on these types of new packaging platforms. So these reference chips are proving to be a very valuable kind of tool in development of packaging solutions. So really, in summary, what we see is photonic packages are becoming much more complex, really driven by demands like AI and co-packaging, where we see a large increase in the number of optical and electrical channels. For example, in optical, we need to go over 100 channels, well over 100 channels into the future. So that's becoming really, really important. Co-packaging with electronics is essential. So for example, developing a common interposer where we support both optical and electrical is really the way forward. And the interposer enables wafer level processes. Glass is ideal because we can start to integrate optical waveguides. So besides having electrical RDL, electrical redistribution layers, we can have optical redistribution layers as well. So fanning in and fanning out these optical waveguides. And critically, developing the packaging equipment to support these wafer level processes is extremely important. So having companies like Ficatech, for example, on site here at Tyndall really enables us to achieve some of those goals. So Jose, thanks very much. I don't know if you want to open it to questions, but that's great. Thank you.
Peter, as usual, we have lots of questions, but this is a collaboration opportunity. You're also going to be in Malaga in 4 weeks with us.
Sure.
Please tell us, what are, in your opinion, the one or two main challenges, the one or two companies, solutions that you will be very happy to find out during this morning?
Sure, sure. Well, one of the big areas that we really need to work on is linking up the foundries, the PICs. So, for example, looking at addressing a common optical interface. So we see so many. I mentioned this earlier on. I do believe processes like evanescent coupling, where we flip the device onto the interposer and we can evanescently couple into a glass waveguide on a common electrical optical interposer. I do believe that's very, very important. It really enables us to address some of these optical interconnect and co-packaging challenges. Micro-optics, very, very important. Micro-optics enable us to move away from bonding fibers directly onto the PIC. So micro-optics and the silicon, the indium phosphide PIC foundry compatibility with the packaging is two top priorities, I would say, Jose.
I will have a lot of questions for you. I'm going to go to the questions, but before that, I need to say hello to a very important person for me. Hello, Puya Dianat from QCI. How are you doing today?
I'm good. I'm good. Hi, Jose. Good to see you here.
Puya was the director of PIC technology at Optica, and now he is with QCI. Can you tell us what QCI is?
Yes, and if I can quickly put something on the screen, but it doesn't seem that my documents are working. Anyway, QCI is actually a Tiflin foundry as well as a quantum computing company, and we are basically leveraging the nonlinearity in Tiflin to realize quantum optimization machine. And the foundry actually is available for the PIC community to use. It's a US-based foundry, and it's coming up later this year. So I would be happy to speak with whoever who wants to use our services or make any devices with Tiflin and try us.
Puya, you did a fantastic job with Optica, and we are so happy to have you now as a corporate.
Thank you.
Optica.
Thank you so much. Thank you.
Peter, the first question for you comes all the way from Info. Jeff Rize, could you tell us what's on your mind? Jeff?
Yeah, hey, good morning. Yeah.
Good morning.
So we produce an indium phosphide chip, and so I'm just curious, flip chipping that onto a glass interposer, for example, if I need to interface to the DSP, how many electrical channels can a glass interposer handle?
Oh, well, you can have multi-levels, so you can have many levels. So the pitch density can be, maybe 100 micron pitch. So you can, it depends on the size of your chip. So potentially thousands is like we've seen. We're beginning to see some very large PIC chips, like really large. So there's no limit. It's the pitch density really is the I suppose the limit here. So if you're looking at maybe 100 micron pitch, so you can work it depending on the size of your chip. And again, it's also how you lay out those bond pads. So really, you can put thousands down if it's needed.
Second question for you, Peter, comes from Gooch and Housego. Stuart McFarker, what's on your mind?
Hi, so we do a number of applications which rely on broader bandwidth operation, usually somewhere around the 100 nanometer range, which is sort of fairly achievable in edge coupler structures with mode field converters. What I'm wondering about is obviously when you deal with micro optics and curved glass interfaces, you're going to have some potentially design complexities involved with making that, giving that a uniform transmission across that same sort of 100 nanometer optical bandwidth. So I'm just wondering about sort of what the capabilities of those micro optics are in that regard.
Okay, an interesting question. We have not seen that issue ourselves. We work, as I said, we work very closely with some of the micro-optic design houses. And I would say that the tolerances that we see, spectral requirements, they're fairly tolerant. As I said, we haven't seen a major issue there. The coupling distances are fairly short. So you're talking maybe about some depth of field or focus. The depth of focus may vary. Would that be one of your concerns?
Yes, we're trying, ideally looking for an absolute minimum of coupling loss into the chip. One of the devices we do is the ophthalmic OCT applications. So in that sort of situation, you've got very high return losses that you're trying to deal with, and maximizing the coupling, particularly fiber into PIC. is quite a valuable
Well, the best
resource.
thing I can say is if you're interested in following up, we can run a Zemax or a simulation just to make, you could probably do it yourselves, but we could check that, especially over the kind of wavelength range you're interested in. But as I said, we have not seen any major problems. You know, the coupling efficiencies would be comparable, very comparable to what we see with direct fiber packaging.
Okay, that's really interesting. Thank you.
Very much, Stuart, and let you know, everyone, that we have lots of micro-optics companies in the room today. So Mark Dining from Genoptics here, Amos Meets from Irradiant is here. Please feel free to comment in the chat and please tell us. We also saw Sandra that commented that 5 micrometer pitch is done today by Jealousies in glass technology. So please write that in the chat and let me continue because we have many more questions for you. The next one is coming from an automotive company. Paras from Valeo, what's on your mind?
Hello, yeah. So I was just curious to know, as I have designed organic substrate layouts in past. So as he mentioned about interposer-based substrates. So interposer-based substrates are expensive as compared to organic-based substrates, and it's also quite hard to manufacture. So in currently in European Union area, which have you collaborated with substrate manufacturers who can overcome the challenges of manufacturing interposer-based substrates?
In glass, is it?
Yeah, in glass and also interposer, yeah, both.
Yeah, well, so this is still a fairly early stage of development. What I will say is glass is also being developed for electrical packaging. And the previous speaker, or there was a comment made about very fine pitch. So, you know, 2 to 5 micron transmission line pitch. That is true in electronics. So we have seen that. What I will say to your question around organic, we have seen warpage issues on organic. When we flip silicon photonic chips onto an organic, we've actually seen, for example, with edge couplers, typically over a few millimeter edge of a PIC, we would see a couple of microns warpage, which is sufficient to induce, you know, serious coupling losses over a large waveguide, or sorry, over a large edge. So organics do really present severe warpage issues. Whereas glass does not necessarily have that. But I think the real opportunity here with a material like glass is the ability to integrate optical waveguides. If you just think about it, if we didn't have electrical RDL, where would we be? We wouldn't be able to do all we can do with microelectronics. So kind of taking that same kind of thought to optical, having optical waveguide and the ability to route on an interposer platform really enables applications. So, you know, I think that's a very attractive proposition. And as I said, glass is one of the materials that is being developed in electronics. We can piggyback, in a sense, by all those developments in the electronics world as well.
Peter, we talk about the need for many channels, and we talk about the need of very low insertion losses. And I think right now there are few companies who are addressing that. As you know, this is a company that matches enablers with integrators. So there's a couple of companies I would like to introduce you. You know them extremely well. The first one is coming all the way from Eindhoven. Simone Cardarelli. Ciao, buongiorno, Simone. How are you today? We are hearing a lot of new things from MicroAlign, and you just heard about the demand from Peter. So tell us how you can address it.
Hi, Jose. Thanks for this this organization of the event and this opportunity. Thanks, everyone. It's an interesting set of slides that I've seen, and I can first maybe, I can ask to Peter a quick question. As we address in MicroAlign high accuracy alignment, so that basically fibers can be aligned in a fiber array within 100 nanometers accuracy, which at the moment we target as application for quantum computing, for example, where also 1% of coupling is important. Do you see for the application that is actually this glass interposer serving, do you see a potential match between the two technologies, or basically this 1% or 100 nanometers accuracy that we provide in that case is an overkill? Can they live together? Or is the high volume glass interposer aiming more to high throughput fabrication?
Yeah, I suppose just from a general point of view, and I'm only picking glass here as one option, and it's something we've been looking at. We are looking at other materials as well. But really, I suppose the motivation here is that the more and more we work on this, we see that we must align with electronic packaging. Like we must align with electronic packaging. So the more we do around processes at wafer level, at flip chip, and so forth, and we use the equipment that's already available and maybe tune it somewhat, I think that's the motivation. And there's some fine details in there, but really, so surface coupling of PICs is really important because in electrical, it's all on the surface. So optics should similarly be on the surface. That's my strong belief. The equipment, the interposers, I really believe that's really the motivation behind all of this. So it's trying to merge both photonic and electronic packaging processes, equipment, design rules, all of these things. I just think that's a good thing. And there's going to be ways that it could be better in using alternative approaches. I do think the package level, part by part, package by package, it's really not scalable. Well, it's not scalable. So when we see some demands of very large volumes, it's just too slow. And so I suppose just at a very high level, the general approach is the alignment of the merging of the ecosystems of optical and electrical packaging is the fundamental motivation.
And also just
Simone,
for me
do
to
you have one slide to show us?
Oh, yes, I have it.
We
I
really
have
want
it.
to see, because we have heard a lot about your fingers moving and aligning to, and you do have the solution that many of the people in the room are looking for. Tell us.
Sure. Can you see the screen?
Crystal clear.
Okay, here we go. So basically, in a few words, MicroAlign is now alive since 2021. We started as a startup that develops, and we are still a startup, of course, that develops microactuators to align multiple optical fibers. And as you see in this video here in the middle of the screen, what we have developed until now is this set of piezoelectric cantilevers that can align each fiber independently in two directions. And the reason for this one is basically to achieve active alignment per fiber, per core based. So each core, we have a system here that can, if we think to edge couple these fibers to a chip or to whatever another optical component, we have a closed loop system that can align each fiber independently. As we noticed that there were a lot of questions around how to fix the fibers, how do we fix them to a chip? The last year, we decided to change business strategy and to go from equipment supplier, let's say supplier of this microactuator, to fiber array manufacturer, where basically it's a fiber array high-end solution where the 100 nanometer, the core, the pitch accuracy is less than 100 nanometers. So basically, if you go from top to down, now what we are developing is this type of fiber array, very important for quantum computing, photonics. I'm very happy to understand with the people today if there are also other applications for it that you see in obvious for this one or now or in the future. As I said, the uniqueness is that each fiber is independently aligned. And if you look at below, we have a comparison between what we think is also our advantage. Today, there are standard V-groove fiber arrays that offer a specific accuracy of the pitch of the core, and that's obviously limited, well, defined, not limited, by the V-groove passive alignment. And what we do is that we do active alignment, and that's what per fiber. So it will. That's the advantage that we think it will give. And I'm happy to share on the left. This is a nice image of one of our first fiber arrays. This is basically in a nutshell MicroAlign. And I have one more question.
Thank you very much for being here with us today. You're going to be also in Malaga. I hope to see you there. And let me also say hello to another person who is coming to Malaga as well, Frank Levinson. Thank you very much for joining our meeting today.
Good morning. Yes, I'm going to Malaga as well. It'll be fun.
You will be the moderator of one of our panels, the investment panel. And talking about the investment panel, I would like to give the floor, Peter, to another company that is a member of Optica and has been raising a lot of awareness on the last year about the need for ultra high-speed interconnect, coming all the way from Israel. Doron Tal, Newphotonics. Thank you very much for sponsoring the meeting today. You also have prepared one slide to show us. Now it is your chance to tell Peter, to tell GlobalFoundries, to tell everyone today what you're doing and how they can help you.
Great presentation so far. Very relevant to what we're doing. So Newphotonics is a fabless semiconductor. We're designer, developer, and manufacturer of PIC focused on the data center connectivity solutions. We're doing 800 gig and 1.6 terabit per second transceivers. So as we build our chips, we're implementing advanced packaging technologies, working with the OSATs and the ecosystem, really in all steps of the process of the post-wafer processing, the substrate, the design, assembly, and test. And what we're doing now is we're really bringing our expertise in optics to innovate in the wafer level testing and solve some of the our biggest and the industry's biggest testing challenges really associated with wafer level testing. So just to let you guys know what we're up to these days.
Doron, I don't think we can hear you extremely well now.
Oh.
Could you maybe speak closer to the microphone or a bit louder?
Can you hear me better now?
Yes, a bit better, yes.
All right, go. So let's go through it again. So about
No, we
Newphotonics.
heard you so far, just to hear you better now.
Yeah, okay. So that was really the one slide we prepared for the discussion today.
Thank you very much, Doron. You shocked the world on the last two OFCs. What is the next thing that we should be expecting from Newphotonics?
Yeah, so we're excited about ECOC next month. We're looking to connect with everybody. We'll be showing off our NPG 102 chips that we'll be sampling next year. So these are coming with silicon photonics integrated solutions for the data center. Some of our optical equalization technologies that are getting integrated on a monolithic die in these chips. This is going to be very exciting for ECOC next month.
Thank you very much, Doron. Back to you, Peter O'Brien. We have a question for you, coming all the way from one of the design houses member of Optica. The company is called Epiphany. John, tell us what's in your mind.
Yeah, again, thanks a lot for sharing these new developments and packages. And yeah, I wonder, even if you make PIC design and free space optics, so it's really, so how would you design it? So because we as a designer, of course, need to think about packaging when we design the chips.
So your question again is how do you split the design?
No, not split the design, but from the PIC design and then going to free space optics, right?
Sure.
So how would you take care of that in the design phase already of the PIC, right? Because when we design it, we want you also to package it in the end. So that needs to be done in the design phase.
Sure. No, it's a good point. So they kind of go hand in hand. So when you're laying out your PIC, really it raises a very important point. When we're looking at a module or a subsystem that's being designed, we really have to kind of work backwards. So in a sense, your PIC kind of is designed hand in hand with your full module. Too often we see the PIC being designed in isolation, and it just can't be assembled and packaged, even with micro optics. So it's kind of it's all done from the in a sense work backwards and work forwards as well. So
no, we work forwards, right?
Yeah, you work forwards, but we work backwards as a packaging team.
But
essentially you work together, and that's really, really important, because if you just work forwards, you'll end up with some crazy package that you probably can't build. So so really, it's kind of like it's a two-step approach, and being able to visualize your module before you start, you'd be surprised. Some people don't. And being able to do that is so important, because the other thing is you need the machines to be able to do it. So working back, in a sense, enables you to do that, the assembling and so forth. So as I said, working with a packaging provider that has the understanding of your PIC, but can visualize how it's all going to be assembled, what the final package looks like. And also something we're starting to work on is cost modeling. So essentially the design choices you make, the materials you use, all those kind of things. And also environmental sustainability is becoming very important, and supply chain, where it's coming from. All these things have to be included. It can't be just a technical exercise.
Yeah, so basically my question was where do we shake hands, right?
At the start. Yeah.
Peter, a couple of years ago, you and me are getting a bit of white hair already on the sides. A couple of years ago, 20 years ago, you and me were at Photonics West, and we're very happy that a company called Technovis had the first PIC-based interrogator of fiber optical sensors at the entrance of Photonics West package by the community.
Actually, Jose, I just put a question out there for people. How are you going to package 1,000 channels, optical channels? Can you do that? So like these are, and it's not going to be a fiber array. So, if you think about it back in the 50s and so forth, the electrical packaging, they're the numbers we're talking about. Now what is it? So we really need to start to think where this goes, because we're kind of painting ourselves into a corner using fairly conventional technologies. So looking at RDL, optical RDL, thousands of channels and even higher potentially, I think that opens up new domains for exploitation. And that's kind of the things we're starting to look at now. We can afford to look at that. So really, presenting that type of challenge to people, where do you go to get thousands of channels on a single chip I'm talking about?
And I think we can only address that with the new community of photonic integrated circuits that is driven by semiconductor giants. And with this, I would like to give the floor to the second speaker. But Peter, please stay with us because we have still a lot of questions for you.
Yes.
But allow me to give the floor to our second speaker, coming all the way from GlobalFoundries, Optica corporate member, and a big fan of Optica because Vikas, you have been at many events this year with us. Vikas Gupta, the floor and the attention of everyone, I'm so happy every time I say this, goes to GlobalFoundries.
Thank you, Jose. Thank you. Let me start sharing my screen. Can you all see my screen? I'm going to put it in.
Gorilla Glass Clear.
Yeah, I'm going to put from the beginning. So, okay, thank you, everybody, for this opportunity. My name is Vikas Gupta. I am the product manager for Silicon Photonics at GlobalFoundries. And given the time is short, I'm going to just jump in. I think I'm just going to draw your attention to the two sort of bullets on the right. I think the growth of generative AI and the power consumption of data centers have sort of fueled the adoption of photonics, and more specifically, silicon photonics is coming out as sort of the preferred solution. The growth of generative AI requires fairly large networks, high speed, low power. And right now, in terms of power consumptions in data centers, as the data centers are transitioning to sort of GPU-based racks, these racks are consuming almost 2 or 3x the amount of power, which is, of course, increasing the footprint and the power footprint of these data centers. So both of these sort of trends are what is driving the photonics industry, and more specifically, silicon photonics. And so from GlobalFoundries, we offer a technology called GF Photonics, and it is a 300 millimeter technology that integrates both, an 45 nanometer class RF CMOS, and you can see the transistors on the left, and a fairly rich portfolio of photonic devices, all integrated on a single piece of silicon. So you can see, components such as modulators, photodetectors, waveguides of different kinds, and then our plan of record fiber coupling solution is the V group based fiber connector. And we do also have a technology and a development for laser attach. But this is, as I said, a very flexible technology because it includes multiple types of modulators, including Mach-Zehnders, micro rings, and this also sort of enables the implementation of both CWDM and DWDM type of applications without any customization of the technology at all. And all of this work is, of course, supported by an electro-optical PDK offered by leading EDA vendors. So it's a fairly rich technology, ready for production and available to anybody who is interested in transceivers. Of course, transceivers being the first application specifically around co-packaged optics, but the technology we will continue to build over for other applications such as LiDAR and such. Now, I wanted to just give everybody 2 slides of updates. And then one of the requests from the Optica team was, where do we help, and what are we looking for from the industry? And so this is sort of where the section of where we can help. I'm going to give you all two examples of technology entitlement. So we, as I'd already mentioned, we have a fairly rich set of components already implemented in silicon nitride. Silicon nitride as a material is athermal, and so there's, on the top I'm showing you multiple components which are already in the PDK as part of our portfolio of devices, passive devices. And on the bottom, we've also introduced a coarse wave division multiplexing macro also. This is actually built out of our PDK components, but this has been validated. It meets the CWDM MSA standard, and we will continue to refine these sort of components. The other one I wanted to just show you all is, I had mentioned that the GF Photonics has both electronics and photonics integrated on the same piece of silicon. And what I'm showing you here is from a technology entitlement, we've demonstrated a 100 gigahertz bandwidth transimpedance amplifier with some high Q inductors that we've implemented in this technology. And again, the idea is to sort of marry the electronics, the analog electronics, and the photonics on the same piece of silicon. This alleviates some of the packaging complexity of having a separate die attached to the PIC, if you choose to do it that way. And in addition to that, we also have a standard cell library in case you want to do some basic digital circuitry also. So going back to the previous conversation that the speaker was having with one of the attendees about sort of the challenge that we face and where we're looking for industry collaboration, there's always this sort of tops down, bottoms up approach to building up systems. So a lot of times the PIC designer will come from, design the PIC, going through, talking about the mounting of the PIC on the board. But then from a system perspective, there may be, requirements from a power consumption, the way these systems are cooled, how much actually room you have within your system. And there is clearly a lot of collaboration that is needed between the designer of the PIC and the designer of the system to be able to come up with a solution that, as the previous speaker talked about, is cost effective, but is also manufacturable. So I think these are areas where, from a collaboration perspective, there's a lot of work to be done in the industry. Given the lack of time, there's another area in terms of test. So a lot of times we talk about test as, being able to test a few PICs, but for high volume manufacturing, a lot of the testing has to be done at wafer level. And I would encourage test houses and test vendors to think of innovative solutions where you can do electro-optical testing, either at speed or even low speed, to be able to get the electro-optical testing done at wafer level. I think that would be a huge benefit for the industry to make these technologies sort of viable for high volume manufacturing. So I think that's pretty much my slide set, and I'm open to questions, so I can come out of presentation mode.
Thank you very much, Vikas. I think with your presentation, especially with the last slide, you really opened the treasure box for all of our members and also for all the listeners, because, right, we have representatives of so many companies. And you've mentioned already some of the challenges within design, testing, and I have to say that we have solutions for nearly all of them. And excellent. I would like to actually already introduce you to one of the solution providers for the wafer level testing. It's one of our corporate members, Keystone Photonics. And Philippe, please share your slides and tell us about your capabilities.
Thank you.
Yes, thank you. Thank you, Vikas, for making the introduction to basically our solution we provide. We're Keystone Photonics, and we provide innovative solution for wafer level testing. And just to motivate why this is so crucial for the whole ecosystem, I'd like to restate that, during the manufacturing, you often start from a wafer, which is the of the product, but only makes up a small fraction, maybe 1%, maybe more, maybe less, of the whole transceiver or whatever product has to be designed. We have a relatively low-cost product in the beginning, expensive product, maybe hundreds or thousands of dollars in the end. However, the silicon photonic wafer has not 100% yield. It's lower than that. So it makes a lot of sense. It's absolutely essential to do wafer level testing to have known good dies. And that's by the way, absolute standard for electronics industry. The market for electrical probe heads and probe cards is $2.3 billion last year. 2023. And now for optics, that's not the case. There's no solution available right now. However, we do provide that solution now. And it is based...
Philip, and you have to share it now. Please share your slide.
I believe I do share my screen.
No, you don't.
Oh,
you got so excited about the testing that you skipped this important point.
Apologies. Yeah, so the key thing is wafer level testing. And we do provide that solution, and it's based on 3D printed micro optics onto fiber arrays. These micro optics can adapt to all situations for wafer level testing. May it be trench level testing, where we 3D print optical periscopes that can also go in any angle, or optics, micro optics, and fiber arrays that are suitable to probe grating couplers, lenses on optical chips. We can also probe expanded beam approaches. So we do have the solution for all these challenges. And this solution is not entirely new. We're doing this since 2017. We're in most or a large variety of silicon photonic foundries, especially in US. We're partnering there with all or most wafer level testing companies, including FormFactor. You can see an example here, but also PICAPP, MBI, and a lot of others. And that work, you can see here that the public presentation from FormFactor is exactly electrical optical testing. So electrical probe card here, optical probe head here, and that's what we deliver. We deliver this metal piece with a fiber array, fully qualified, fully suitable for testing of 64 channels and more if needed. Production ready. We can go to very narrow pitches down to 25 micrometers. We can probe with very low back reflectivity, broad wavelength range, whole communication band. So it's all there. We're in manufacturing, and we're happy to get in contact with you.
How does that sound to you, Vikas? Something interesting? Because you've mentioned
Yes.
that the wafer level is something that we all that it was be one of your demands.
That is correct. I'm actually going to reach out to the speaker once we're done.
It's actually very important to remind everyone in the meeting that after this meeting, you will get the roster of all the participants. And please, members, let us know with whom from this meeting you would like to get in touch, and we'll make sure that this will happen.
Yeah, this is pretty impressive. Yep, thank you.
Thank you so much. And actually, Philip, could you please stop sharing your slide?
I'm better at that.
Excellent. And then you also mentioned, that the other challenges, because when I look at this, especially at the design of the schemes, right, and when you mention so many challenges, or when so many components that are packed on one certain circuit, it comes to me always the question, how about the alignment? What is, how precisely you have to be and in which direction you work? Would you comment something on this, Vikas?
Yeah, I think so. So clearly, depending upon the mode size of a single mode fiber, it's about 9 microns, and there are technologies out there for mode conversion. Now, the challenge is as you get from the mode, the 9 micron mode to the nanometer sized waveguides, the smaller you make the mode, while it couples well with the waveguides, it just increases the complexity of alignment. So it's a trade-off between cost and speed for high volume manufacturing. And right now, our base technology, as I'd mentioned, is sort of V grooves. I think the previous, I think one of the attendees had talked about the misalignment of the core. So those are challenges that that need to be addressed. What is not clear to me is whether these need to be addressed through design or whether they need to be addressed through manufacturability, because there will always be areas. I mean, as you go into high volume manufacturing, there will always be some slop in accuracy of any production material. And the question becomes, just like we do on the semiconductor side, where designers will design to corners, worst case corners, and so it's not always clear to me where that line is between designing for the worst case corner versus making sure that you have the best manufacturing alignment capability, because that comes at a cost. And I think, as the previous speaker talked about, it's always interesting to come up with the latest G-Wiz technology, but if it is not manufacturable, it does not meet the cost targets of a system. Those become G-Wiz technologies. They don't go into high volume manufacturing. So as a foundry, what we are looking for are solutions that allow us to go into that high volume manufacturing capability. Otherwise, foundries can't exist.
But there are always, with the alignment, there are two big camps that are, I think, a little bit on the more active fight against one another, is the passive alignment versus active alignment.
So as a foundry, we have to support both. So actually, our V-grooves can do both. So we have technologies for the V-groove for passive alignment. What we don't talk about openly is that those V-grooves, if you make them a little wider, can also support passive active alignment. So we don't have a preference per se. A lot of times it depends upon the customer based on how they want to stack up their system and build it up. V-grooves are capable of doing both passive and active alignment.
I would actually like to hear about this question that you raised from two of our members that are both one doing passive alignment and one doing active alignment. So let's see what they say and if you'll get convinced. So I would like to get, for instance, to the floor to call out Martin from Finetech. And tell us, Martin, what do you think about the passive alignment, V-groove and passive alignment for mass manufacturing?
Hey, hello.
And share your slide.
Yeah, thanks for having me. And yeah, closely following the discussions, very interesting. And yeah, let's go for my slide. Here you go. So yeah, we are.
Martin, I think the sound disappeared. And I think Martin disappeared. Well, then and hopefully he will come back smoothly. We have several of his colleagues in the room, but okay, let's maybe.
I'm trying again, so I'm in again.
Yes, Martin, you're back.
Give me a second chance, please.
Okay.
Once again, is that working now?
Yes.
Okay, thank you. So welcome from Berlin. So we produce high precision equipment, and following the discussion, it's like chicken and egg problem. So we built the tools that are for developing these kind of technologies, finding good and bad ways, and also transferring it into a possible fruitful production. Yeah, passive alignment this is where we come from, and it is very interesting coming from the electronics world, trying to adapt all these things also in the optoelectronics. When it's about discrete components, makes sense. When it's about more integration layers, integrated photonics, still it's good. Best alignment is the alignment that you don't need to do. So all kind of self-alignment approaches are, of course, best, but we see that there are constraints. And so there's always a point where you need to do some coupling and maybe also combining electrical connection and photonic coupling in the best way. So following the what you see is what you bond philosophy of aligning structures and getting a very good alignment and post-mount accuracy it doesn't work if the light goes a different path than your optical key features. And I think this is the point. If you manufacture the components in a way that you can trust in what you see, this is reproducible, then you can use passive optical alignment and bonding. We have an intermediate approach as well. So if you know the offset, that you use some helping structures to get the parts aligned, and you know, like known good die testing, known offset bonding, that you can feed that last nanometers of getting it into the sweet spot, you can still go with the optical approach, having the passive alignment. And if this doesn't work, of course, then last resort would be to use active alignment. And also, I wrote it down here, it is even possible also for us to combine passive and active alignment, doing a perfect pre-alignment and an active alignment that is only pushing the last couple of nanometers. And we are really looking for like the design rules and how these components will look like. So will it be edge or surface coupled, and how you combine the electrical and the optical paths, and also how it is possible to make that pre-testing to find out the matrix. So this, with our machines in the R&D world, it's possible to just test things and do biasing of offsets in a strategic way, and then feeding into this in a database, and for the production, then just use the known offsets. But this is only one single point. This is such a vast field, and it's very interesting for us to see all this being combined and using the traditional bonding technologies. So we are part of that game.
Thank you so much, Mark. And I have to say, you know, when you've mentioned that there's a very exciting field, yeah, we have 240 active participants that are listening to us now. So it's clearly an indication that there's a very interesting field. And before we make our judgments, let's also hear from the camp of the passive alignment. Gianni, what do you have to say? The V-grooves and the passive alignment. How does that look and work together? And please share your slide.
Yes, I try to. Hi, everyone. First of all, let me share my screen. I hope it works.
It does.
So basically, okay, if you need my personal opinion,
let's start with this one.
So my opinion is that what Peter presented, the integration and the interposer approach at wafer level, I think for the next year has to be really well developed, because all the other, even if it is against Visio Robotics expertise, let's say, because this part of flip chipping, die bonding, wafer bonding, also imaging wafer bonding, I think it could be a solution for the future if some sort of volume will really happen, and integration as well. In relation to your question, big grooves, not big grooves, you know, I'm from my experience, it takes a little bit of time. For volume application, I don't think that this is so straightforward. So this is my personal opinion. So it's a little bit tricky to really do at volume, as it's not like to say. In relation to Visio Robotics, that is a different thing. What Visio Robotics do is essentially try to use, as you see here in the slide, different...
Can you please share, Gianni, sorry to interrupt, can you please share the slide in the presentation mode? Because I think we all see it in editing mode.
I think okay.
Yes, you also got drifted away with the discussion of the possibilities and forgot to click the button. Please present us.
Yeah. So basically, you see, we have different tools. We are working in many different fields. Lately, we are focusing more on photonics for realizing systems that can allow the alignment and the pigtailing. So essentially, we try to use our expertise also from different areas like automation, robotics, and high precision design, the software. We realize our own software. We have different solutions that we developed in the years and we are trying to offer to the potential customer a dedicated tailored solution for this kind of application. So alignment can be fiber array alignment, can be lenses alignment, can be interposer in a certain sense, and using the tools that you see here reported. So we have different toolboxes. We have a lot of flexibility. We are small, so we are not, let's say, it's difficult to fight against bigger and more structured companies, but we offer this tool expertise for, let's say, tailored solution. If someone has some specific request that can be solved together, we have all these different tools and we can realize the machine or the system, whatever is necessary for serving in time, of course. We don't need 2 years to realize the system, so we are quite quick. And this is what Visi Robotics does. So be aware that we exist, we are flexible, and we can support in a very quick way the necessities that can arise.
We are aware. Thank you so much, Jenny.
You're welcome.
So Vikas, so after you've heard passive active, what are your judgments? Tell us.
Yeah, so as I said, as a foundry, we are a service provider. So a lot of times, a lot of these decisions are made by our customers. However, I think the more important part is, as a foundry, we have technologies that are flexible, that can support, passive alignment and active alignment. All I can say is, passive alignment becomes an important consideration when you start talking about things like co-packaged optics, where you're talking about almost 30, 40 fibers that are aligned to the edge of the PIC, and at that time, the time that is required to do active alignment per fiber becomes prohibitive. So once you start talking about fairly large fiber arrays, I think the passive alignment becomes a more attractive option. But I also want to state it's not the only option. So so that's sort of where we are, and while vGrooves continues to be our plan of record, we are open to other technologies that customers may need. Fundamentally, we are a service provider, and we need to make sure that our customers' needs are met.
Yeah. We actually have a question to you, Vikas, from Amir from Lithium.
Sure.
Amir, you raised the question, so please unmute yourself and ask.
Yeah, thank you so much. So this was can you hear me?
Yes.
So this was actually the question to Philip, and then the awesome pre-scope technology. So I was wondering, how do you handle like polarization? I mean, can you is it compatible with PM fibers or?
Yeah, we use PM fibers. That's the easiest way of handling polarization.
Okay,
and then you get a 20 dB PR. 20 dB PR is then the outcome. So
okay.
Yeah, it's enough for most applications.
Yeah, 30 is good.
Okay, and I guess that was the similar question from GmbH, Stuart. Stuart, I guess you asked about polarization manipulation components, but I think this is more for the, again, for the Keystone, or? Stuart?
Hi, my question was, I think I sent that question in while
Yes.
Vikas was speaking from GlobalFoundries when
Exactly.
you
So
showed the list of components in the that were available. So I was just curious about the sort of other devices that might be possible for sort of polarization multiplexing or demultiplexing.
Right. So yeah, this because the time was short, I didn't go into all of the details. So we do have PSRs, polarization shifter rotators, already pre-characterized and in our PDK. So if you're interested, once we get NDAs and things like that in place, you can have a look in the PDK. So all of these, and that's the point I was making in my presentation, that the GF Photonics technology is very rich. I showed you all a very small subset of just the passive components that we've included in the PDK, and the CWDM macro, as I'd mentioned, is sort of the newer component. But there is a fairly rich component library in the PDK already, which includes shifters and rotators. Yeah.
Thank you, because and you also mentioned, that you're also looking at the designs. That's something that eventually, which merges the manufacturability with actually the desires of the customer. And we have a member who is OptiWave. Cem Bonfil is here to maybe show some of their solutions and capabilities. Cem, please share your slide, unmute yourself, and present how you can help of making even some of the craziest desires of the customers true and manufacturable.
Okay, I hope you can hear me and see my slide. Okay, so I am the product manager of OptiSpice at OptiWave. I'll give you a brief introduction of the company and then talk about how we deal with parameterized compact models internally and the products we're going to be releasing. So OptiWave has a wide product portfolio of simulation tools ranging from device level to circuit level to system level. The applications include optics, datacom, telecom, quantum sensors, and many more. We also have a new product called OptiInstrument, which can be used to automate test equipment. Now, the topic I would like to go over today is the creation process of process-aware compact models for PIC design. We'll be releasing a series of tools to automate this process, but our initial focus right now is on the passive devices, and we'll be adding active device modeling in the future. Now, as you can see in the slide, we start with a parameterized GDS2 mask. And then combining that with material definitions, EM simulation, and a design goal, now it's possible to automate the compact model generation, finding the optimal layout for the optimal performance. Now, additionally, since the layout is parameterized, it is possible to run sweeps to include a solution space around the optimization point. And collecting all this data together, you can then create a compact model that is process aware through either interpolation, parameter fitting. You could even use neural networks and many other methods. This follows the idea of how you would generate a compact model in electronics. So we need to repeat the same process in optics as well. Once the compact model is ready, then it can be used in PIC layout for circuit level simulation, which can include first, obviously, regular design performance check, Monte Carlo analysis, and sensitivity analysis. This is critical to discover issues in early stages of the design process and reduce sensitivity to variances in fabrication. Now, in the next few months, we are launching a new tool that automates the generation of S parameters from GDS masks or a GDS generator script. This tool will include various different solvers capable of taking advantage of CPU parallelization and GPU acceleration. Additionally, these solvers will share a common platform that automates port detection, extrusion, and source and monitor placements. We'll also be supporting port symmetry to speed up the simulations even further. Now, just as a summary, we're working on accelerating PIC creation process by automating the compact model generation and supporting first-time right design. Our design philosophy can be summarized as let the computer do the work. We would like to hear about obstacles everybody's facing during PIC device design, specifically related to compact model generation, because this involves fabs and also people who are designing PICs. And so that we can incorporate real-life challenges and into our products. So please free to contact us and let me know about your questions about the process.
I'm sure there will be interested ones. Thank you so much, Cem. Vikas, does design always come from the customers, or do you also have a say that you can think, okay, when you look at a certain request and you believe that it can be done better?
Yeah, I think we do have a very collaborative way of working with our customers. Clearly, there are certain designs that are more manufacturable than other designs. And so, first of all, of course, we do have DRC decks that allow the customer, the first order of business to check and make sure that their designs are DRC compliant. And the DRC actually comprehends curvilinear shapes for photonic design. But yes, we do collaborate very closely with our customers. We have capability of doing link budget simulations. Our PDKs allow for Monte Carlo simulations, across devices and process variations. So yes, we actually provide feedback to the customers in their design phase with respect to designs that are more manufacturable, taking into account packaging, process variability, et cetera, et cetera. So I think yes, we do work very collaboratively with our customers.
Thank you. Thank you so much. Well, let's move on, and because now from the entire wafer, we start to go into the small components. And I would like to introduce all the way from Japan, one of the speakers that are actually working on the development of the integrated circuits and also different device-based PICs for the telecom datacom. It's my great pleasure to introduce Sumitomo Electric, and Yasutaka-san, are you here? Please.
Yes, I can
The
hear you.
floor and attention of 230 people belongs to you.
Yeah. Thank you very much for the kind introduction.
Please go into the presentation mode.
Yeah. Can you see the presentation?
Yes.
Yeah. Okay, so my name is Yasutaka Mizuno from Sumitomo Electric Industries in R&D department. So today I will talk about the 3D printed beam expanding lens for chip-to-fiber vertical coupling. So the lens images are shown here, and we demonstrated low coupling loss, wide alignment tolerance, and reflow reliable optical coupling technology. So I will start from background. As you know, co-packaged optics is attracting attention because it can significantly reduce energy consumption. Chip-to-fiber coupling is essential component for CPO, and low profile, detachable, and reflow tolerant technology is desirable. So there are two types of optical I/O for silicon photonics. One is edge coupler, and the other is vertical coupler. The example of edge coupler is inverse taper. It has superior performance for coupling efficiency and wavelength bandwidth, but it is not useful in terms of packaging because alignment tolerance is very narrow. Fiber coupling is limited to 1D configuration, and the inspection is only done after singulation. In contrast, vertical coupler, such as grating coupler, is inferior performance rather than edge coupler, but it is useful for packaging because it could be arranged in 2D configuration, thus increasing the beachfront density. Also, the inspection of PIC could be done in wafer state. So to take the advantages of both couplers, we devised an edge coupler with free-form mirror. The concept is simple. Reflective mirror is formed onto the edge coupler of PIC. Light is emitted from edge coupler toward horizontal direction, and then it is reflected toward vertical direction by the mirror. There is a similar mirror on the fiber side, so the light is reflected again toward horizontal direction. The key function of this lens is beam expanding by the convex shaped mirror. Typical edge coupler has MFD of only 3 micrometer, so the alignment tolerance is less than 1 micrometer. However, the output beam from this lens is as large as 40 micrometer, so the alignment tolerance is broadened to plus minus 10 micrometer. So in order to demonstrate the concept, we fabricated the lens with nanoscale 3D printing technology, collaborating with Vanguard Automation. So first, PIC is immersed in the uncured liquid resist, And then 780 nanometer laser light was irradiated to the resist to selectively cure the lens shape. In this time, the position of PIC waveguide was detected, so the lens was formed at its focused position. After laser irradiation, the lens was formed onto the edge of PIC. Finally, uncured resist was washed away by the organic solvent. The printing power line is 4 minutes for prototype, but it could be further reduced by optimizing the printing condition. The right side figure shows the SEM pictures of fabricated lens. We can clearly see the very smooth lens surface. Then I will move to the measurement results. At first, we measure the coupling efficiency between PIC to fiber. In this measurement, the output port of PIC is silicon nitride SSC with MFD of 3 micrometer, and that of fiber is 10 micrometer. So MFD matching is done by the design of this convex mirror. We can clearly see the flat characteristics over 100 nanometer range, and the typical value is minus 1.8 dB at 1550 nanometer. The right side table shows the coupling efficiency of 9 lenses before and after reflow thermal stress. We can clearly see that the coupling efficiency is very stable after reflow. Also, the deviation of each lens is very small, with a standard deviation of only 0.03 dB. So we fabricated these lenses by 3D printing, but the reproducibility and reliability are pretty good. So next, we measure the alignment tolerance between PIC to fiber. The left side graph shows the alignment tolerance along in-plane direction. We can see the broad tolerance, and the 1 dB tolerance is plus minus 10 micrometer as designed. The right side graph shows the out-of-plane alignment tolerance. Surprisingly, the coupling efficiency is almost constant from 0 micrometer to 600 micrometer, and the excess loss is below 0.5 dB. So I will show you the pictures during the measurement. In this case, the distance from silicon photonics chip and fiber is 600 micrometer, but the coupling efficiency is less than minus 2 dB. So we think that the wide alignment tolerance could be very useful for detachable connection. So finally, I will summarize my presentation. We proposed vertically coupled beam expanding lens for PIC to fiber connection. Prototypes were fabricated using 3D printing technology, and the coupling efficiency of minus 1.8 dB and 1 dB tolerance of 10 micrometer were achieved. And the performance of this 3D printed lens was unchanged after reflow thermal stress. So thank you for listening.
Thank you very much for being with us today. It is great to have this showcasing on compatibility when we hear from Sumitomo and Micronics. And I think the best way to follow up this presentation is to give the floor to the representative today from Vanguard Automation, Micronics. Thank you very much for being with us today. Laura Horan, tell us what's on your mind.
Thank you, Jose. And thank you, Isaku, for giving a nice presentation on our technology. Let me just share my screen. Okay, so in presentation mode. So I want to thank all the speakers. We really highlighted the key challenges in the industry for photonic integration and packaging, particularly for PICs. And at Vanguard Automation, we focus on a solution using very low precision, pick and place of passive alignment and additive manufacturing using 2D laser lithography. So in the last presentation, you showed a clear example of how this works. So we have a range of solutions to provide photonic integration using additive manufacturing 3D laser lithography. The first of these we call photonic wire bonding, which is
Please continue.
Which is a freeform optical waveguide, which can be used to couple different components together. You can see on the far left-hand side the solution for coupling multi-core fibers together with a high interconnect density. And in the center, the solution for coupling fiber to chips. We also have a different solution called fast-attached micro-optic lenses, which was shown in the last slide, which can be used to relax alignment tolerances, all done with 3D printing. And Vanguard automation really focuses on having low insertion losses, but also products with high yield, reliability, and repeatability. We provide this with a complete industry-proven solution, comprising of all the machines, software, material, processes, and full customer support that our customers need to bring photonic integration into their production lines onto their packaging service providers. So in this slide, I'd like to focus on the multi-chip hybrid integration solution. So we've shown many different examples over the years of how to use the technology for photonic integration. And in the slide at the bottom, we have just 3 examples. First, the recent paper on the far left from ECTC, done by RIT, Rochester Institute of Technology, GBC and Vanguard this year. And they showed for the first time a hybrid packaging of an active device integration. So they placed passively lasers onto the AIM chip, reference chip, and connected these lasers to the chip using photonic wire bonding. And at the output, they also connected via photonic wire bonding the chip to a fiber. And in total, they had for the 4 different interfaces, so laser to chip, chip to fiber, a total of 4 dB losses. So low loss, high reliability, connectivity using active device integration, but also relaxed phase tolerances. In the center is another example from Simone Electric, where they have tested the technology and proven it for high reliability using the telecordia testing for damp heat, flow soldering, shock testing, and high power. And lastly, our ecosystem partner, Newphotonics, has been using this technology for years to do packaging for their customers. And recently, they have announced that they have got an 80K with Tower semiconductor for doing photonic wire bonding from fiber to chip.
Laura, I am so impressed with the phenomenon of two-photon polymerization today we have in the room. I mean, we have also a Nanoscribe, we have Heteromerge, we have so many companies really making a revolution on this. I would like to go back to Yasukata-san. As the end user of this technology in the semiconductor business, what is the next thing that you wish to have from two-photon polymerization?
It's our biggest biggest problem is touch time for the micro lens, because we have to print the micro lens onto the silicon photonics chip with as many as 100 channel for one chip. So our wish is to write the one lens less than maybe 10 seconds or only several seconds.
I think we may be thinking about a really big research project here. I believe that we have some people from imec in the room. Philippe Soussan, are you with us today?
Yes. Yes, I am.
Thank you so much for joining, and it is great that your CEO is also going to be in Malaga in 4 weeks. I can't wait. I really can't wait for the event in Malaga, the Global Photonics Economic Forum. But today we're talking about packaging, testing, manufacturing of PICs, something that you know at imec really well. You also have shared, you're going to share with us one slide. Tell us how imec can work together and solve some of these key challenges that companies like Sumitomo and Global are showing today.
Yes, so I will show one slide about what we do, and then I can answer your question.
Go ahead.
Yeah. Just looking for the right window.
I am extremely happy that imec is very active in our meetings lately. And after the meeting that we have in Newchâtel a few weeks ago, many of the companies have told us how great it was to discuss with you and to follow up afterwards. So thank you very much for following up on all the leads.
Very good.
I don't want to put much pressure on you, but please find the find the window. In the meantime, let me say hello to Dan Pitt from Excelleprint, a partner of imec as well, and doing fantastic job on the microtransfer printing technology. Great to have you with us, Dan. I think you're also coming to Malaga in a few weeks, so thank you very much for this. Also great to have in the room the company Lithium and the Thin Film Lithium Niobate Foundry Services. You guys are making it strong. Thank you very much for that. I am ready.
It should come. All right. Do you see something?
Not yet. Bottom of the Zoom window, green arrow up, then press it and then select the word, the screen that you want to share with the word of photonics.
Now you see.
It's here. Thank you so much.
Okay, so yes, packaging and testing, it's a very good point, but first I'll introduce what we do. So essentially in imec, we have an history in a crystalline SOI platform and silicon nitride. We have two versions of this platform. The 200 millimeter is actually available today for mass manufacturing. We're able to demonstrate up to 200 gigabit per lane with this technology. We are building the 300 millimeter that is as well available for prototyping. And when we talk about the upcoming developments, well, first we have the next generation of modulator technology for 1.6 tera and above. And we are working on edge couplers and lasers. So it's actually, we are trying to make a consortium. We are using the Phantom Delta consortium right now to build a supply chain to enable the flip chip integration of lasers on our EC platform, as well as we are promoting edge coupling. Today, the industry has a baseline for vertical coupler. And it's also very difficult for people to use the real estate to make big roofs and other kind of area consuming devices. But we believe there will be a generation that will come with edge coupling because when it comes to link budgets, that is the best situation. So yes, we are trying to build this supply chain for heterogeneous integration. We're in the R&D consortium, different EU projects, and we'll be happy to see what we can do on that matter. I want also to mention two other platforms that we are going to release. So next year we are going to have the LPCVD silicon nitride platform. And the market, obviously the first one is driven by Datacom AI. I mean, there's a large bump and people actually are chasing this type of technology as well as the power efficiency of this technology. But for the second one, the LPCVD nitride, we actually are seeing a lot of opportunity in quantum and in sensors, including biosensors. And in that kind of technology, which is today only passive, we are going to integrate as well the edge coupler and the laser. We want to actually piggyback. So once the supply chain, and that's actually, I'm advocating for whoever and I know PHIX is online, can enable the first one. We'll also then build the supply chain to enable the later on the LPCVD nitride. Just for the sake of completeness, since it's a PIC manufacturing event, we are producing. There are some public announcements that were made a few years ago. If you browse into the news of imec, you will see that we have actually put silicon nitride technology directly on CMOS, directly on imagers. And this is something we do as a custom development. It's for niche application, it's in health. So these people today are not really looking into rationalizing, let's call it the incoupling of light. We are talking about visible, so the availability of sources to put the elephant in the room more visible is also a problem. You know, people like to have red and green, and as you all know here in this community, green is not easy to find. So yes, it's a bit niche, it's a bit tricky. Today's niche. And again, if one day we are figuring out how to put the light sources directly on the silicon, there will be as well an opportunity for cost reduction to take this niche application to more affordable pricing. So that's all I wanted to share with you.
Thank you very much. And I can tell you one thing very quickly about this silicon nitride on CMOS. I would like to always compliment imec from the work that you're doing with the startups. And I think Doron Tal is watching this. What you're doing with AOTech is really very, very impressive. So congratulations on that. One thing, you said that you had an answer for Sumitomo.
Well, yes. So related to the packaging, we are trying to integrate the laser into our library of components. So we need to qualify the supply chain. Right now, we can enable that for prototyping for moderate volume, but the actual industrial supply chain, we are also working on it.
Thank you very much for that. I can tell you from Sumitomo, we're talking about lots of micro optics going on silicon photonics, and there are still many materials challenge to cover there. For that, it's very important to have in the meeting today Alexander Harvig from Delo, who in the offline have been discussing about the need for new material with different refractive index for silicon photonics. Alexander, thank you very much for being with us today. You have also one screen to share with us and with many of the potential partners and current partners that are in the room with you today.
Thank you very much for the kind and nice introduction, Jose. So just, I hope you can see the screen. Does it work?
Exactly.
Nice. Okay. So just a brief introduction to our company. So in general, we are an adhesive supplier located in the southern part of Germany, so close to Munich. But we are worldwide operating, having subsidiaries in US, Boston, Singapore, and in Shanghai. And we have a broad product portfolio, which is basing on 12 chemistries that we are using. So not just acrylates and epoxies, but 10 others. And we are using different kinds of curing mechanisms with our adhesives, but still we are really focusing on light curing. And this is, of course, because catching up the production speeds you typically have for mass production products. And we have a very intense, I would say, dual curing adhesive portfolio, means that all of these curing mechanisms can be combined with light, so that, for example, a 2K curing adhesive or a heat curing adhesive can be light fixed in a previous step, which makes the process very fast. And our experience lies really in optical bonding. So we do a lot of optical bonding, for example, bonding of camera modules where a highly precise active alignment is used. So we are talking about consumer camera, but also automotive cameras with high reliability requirements. Our adhesives can be used also for the production of optical elements like DOEs or MLAs, where we are typically using a nano imprint lithography as a process. Then, of course, we also have broad applications in the electronic packaging business. And with this expertise, we design products also, of course, for the PIC packaging. And doing that, we are mainly concentrating on the optical coupling, so means by use of edge coupler, grating couplers, also use of micro lenses. We also do passive alignment with the V-groove bonding, or we deliver systems which enable the passive alignment. This is the right term to say. But also, let me say, more or less standard packaging processes like strain relief or die attach, for example. And I just wanted to highlight that we always try to develop together with the customer really the best technical solution. So we have a big engineering department and try to collaborate on a deep technical level with the customers. And in a lot of cases, we then design really a customized product for the customer's need. And this is, which I wanted to conclude, that we are very open to collaborations. And if you see anything technically challenging where you think that adhesives can solve the problem, please let us know, just get in touch and we can see what we can do for you.
Alex, we have received lots of good feedback from companies who have interacted with Delo, sharing their needs for materials and the way that confidentially things have been treated is you're a great partner with the material side. Yasukata-san, do you have any question or any wish for a material company like Delo in terms of reliability, refractive index?
Yeah, we have many types of adhesives for the optical device. However, almost all the adhesives for optics is very weak for the high temperature. So we need adhesives which can tolerate to reflow temperature, maybe 260 degrees C. Is it possible for you?
Yes, it is possibly, and currently this is, I would say, the most important requirement in terms of reliability. We are focusing on really to be reflow compatible. We have already certain products which are already tested, for example, also in collaboration with Peter O'Brien's group, where we have focused really on reflow compatibility. So there are off-the-shelf products, so we can get in contact.
Oh, yeah, very interesting. I would like to get some samples.
Yes. No
Yasutaka,
problem.
I gladly pay for the shipping expenses of those samples from Munich to Tokyo. Let me come back to the revolution of two-photon polymerization. Another company from this revolution is Nanoscribe. Jörg, thank you very much for joining the meeting today. You also have one slide to share here with the semiconductor and photonic integrated circuit companies. The floor and the attention of everyone goes to Kasruher.
Yes, hello everybody. I'm happy to be again in this PIC meeting. It's been a long time. Can you hear me?
Loud and clear.
Okay, it's been a long time that that there were no meeting on PIC. I'm missing it. I missed it a little bit over the summer. So nice to be back again. So indeed, Nanoscribe is 15 years old. We introduced the two-photon polymerization technology to the market. And in the last years, we developed it further to be able to print reliable and precisely optics for photonic integrated circuits with our 3D printing equipment. We also made a big focus on enhancing the usability of the system, reducing the losses of the optics which are printed. As you can see here on the slides, there are different examples of elements printed with our system. So you have an example of different geometries. I'll just have to highlight the laser pointer. Examples of geometries which can be printed from periscopes, any kind of periscopes, collimating lenses, focusing lenses, similar to what Yasutaka-san showed. Here are direct edge couplers, for example, for free space, or this is wafer level production of several hundreds of broadband coupler for quantum applications. And we have received some peak performance of less than 0.80 dB coupling, 5 microtolerances. So these are all parts printed with our systems. We are not a job shop. We are a microfabrication system supplier. We can print quite fast. So I think 10 seconds is an interesting challenge. Yasutaka-san, we will take it. Depends on the design. So again, design is important. At the design, you define the packaging. I think this came up during the meeting a couple of times, and especially also for these optical interconnects. If you design the mode field diameter correctly on the chip already, then you can also, I think, go to 10 seconds of print time, for example, for these kind of things. So anytime, if you have questions or if you want to do a print test, come contact me. Meet us ECOC. We will be there, have a booth. We'll have a short training, hands-on training after ECOC. So I can send you an invitation out to everybody, as in the PDF which we shared, there's a link to this.
And you're also coming to a reception at ECOC in a couple of weeks. I'm looking forward to seeing you there. I would like to say to everyone, thank you so much. We are, of course, sold out for that reception. Thank you for the interest, the whole industry, to being with us today. But allow me now to shift gears, Yasukata-san, in this meeting. We have been talking a lot about the packaging of materials, but very often we also need integration with discrete components. And for that, we wanted to have a company that has been leading the development of detectors in our industry, Alvis. Thank you very much for being with us today. Tell us how you want to support the industry, Christoph.
Hi, thank you, Jose. Thank you for hosting us. I can maybe share the window that I've prepared. Maybe you can tell me if you see it.
Very clear.
You see it?
I saw it for a millisecond.
Can you see the screen?
Let's wait. Yeah, start pitching, and I will tell you when it's here.
Yeah, okay.
Well, we don't see your detectors yet.
Not yet?
Not yet.
No, I have some connection difficulties.
In the meantime, allow me to say that after this presentation, we will understand what our friends from Seiku do, and then we will go finish the meeting with PHIX, with the European OSAT, and understand a bit how we all can help them with the packaging and test. Can we try again, Christoph?
We'll try again. Sorry for the delay. It's an internet connection issue.
Now it's here. Tell us.
It's here. Oh, perfect. So I want to present you Albis Optoelectronics for the person who does not know us. We are designer and manufacturer of 3.5 photodiodes and avalanche photodiode. And our products range from the high quantum efficiency photodiode up to the high speed 200G photodiodes. We have 20 years of experience and we have sold 40 million of photodiodes, so we're on the field for a long time. And the message I want to share is that the Albis offer is mostly a top performances, but also connected to the PICFoundries and PIC platform. We have a lot of various optical and electrical interface that can really fit the application that you need. And for this, I picked two examples just to show you. We have this photodiode on the left that is with a backside integrated lens that really facilitates the optical coupling. So it could be a passive alignment in that case, as it has been mentioned before. And we have another kind of photodiode that is more trendy right now, is the mass transfer photodiode that goes to microtransfer printing, for instance, which is targeting high volume and high integration directly onto the waveguide, so with evanescent coupling, for instance. And as it has been mentioned, and everybody is aware, I think everything goes to the end application, and we have usually a solution for each customer, but we have to help the customer to find the right product on our portfolio, which is quite broad. So please contact us if you have any application, and we'll discuss what.
Thank you very much for that, and thank you for being here and all your support. I'm also going to see you at ECOC in a couple of weeks. And allow me to finish this round of quick introductions to our end users to meet Alex Wu from Suruga Seiki. Alex, thank you very much for being with us today. And before we give the floor to PHIX, could you tell us what you do and how you can support Sumitomo and the other end users?
Thank you, Jose. Yeah. Good morning and good afternoon. Because I'm located in Taipei, Taiwan. Yeah, so my time zone will be almost midnight, but it's no problem. Yeah. So let me share my slides and also give the quick update for you, ladies and gentlemen. So.
I love when a meeting is global. You have people in every time zone. We have people in California today, and we have people in Tokyo, like Yasukata-san. It's really great to have a meeting like this.
Yes.
Suruga Seiki, we're getting your slides.
Yeah, I'm sorry. I'm searching for my slides, or Jose, can you please use the slides that I shared to you previously?
Yes, of course I can do that.
Yeah, sorry for that. Yeah, because I'm using my mobile phone. It's a long meeting.
Jose,
so
you want to go ahead and share, or would you like
my
us
battery
to?
was running out of the battery,
No
so I use
problem.
my mobile phone right now.
My team will share them. So if Grace or Tanya is sharing them with us, and then you
Tanya, yeah,
you
appreciate
can just say
Tanya.
next slide
Okay.
after every slide.
Thank you very much, Tanya.
Go ahead.
Okay. Yeah, thanks again. Yeah, sorry for waiting, ladies and gentlemen. Yeah, this is Suruga Seiki Alex Su speaking. I'm located in Taipei, Taiwan. Taiwanese, but basically we are 60 years old, Japanese-based company. So what is Suruga Seiki doing? That we are new member to the Optica, and also appreciate the invitation from my good friend Dr. Jose Pozo. Basically, Suruga, we provide from the 6 axis alignment key components to the entire PIC system. So this is for the co-packaged optics or fiber array unit assembly machine. So simply speaking, we provide the key components or the 6 axis alignment stage. This is quite similar with the Germany-based company PI. So as everybody know that, PI, they are providing the HESAPA, the Stuva model, good 6 axis parts. So their structure of the motion control is different from our company, but basically we are using the motorized stage plus our algorithm and also plus our controller, so that we can do the motion control and to develop the similar function with the PI. But other than that, we are not only providing the key components, we can use our stage and also controller, and then we can make it into a wafer tester or the PIC fiber array unit machine for the advanced package for the CPO or the optical I/O module. So this one will be very similar with, as you might be also very familiar, because from the first speaker, we also saw that a lot of the system introduction related to the Photonics. And that's also a very, I think they're also a honorable complaint from the Germany, and also yes, our competition, but also our partner, because some of the Photonics system they start to use Surugashiki stage, starting from recently. So basically, for the Suruga, we provide the key components into the entire system. So this is for the photonics industry. And you can see for the flow chart that I draw here, from the chip design for wafer foundry, and then for the wafer cell and burn in, and for the functional test, and also for the PIC module assembly. As you know, this is kind of the workflow that everybody know that will be conducted or implemented in the OSAT. So for the EIC system, we can provide motion parts for most of the global EIC machine makers, such as even the ASML or ASM or Applied Material, this kind of a giant company. This is for EIC chip. And for PIC, as I say, we provide the machine and also the alignment systems from the R&D for the mass production. And sorry about that, but you can see from the right bottom side of these slides, actually, I should zoom in, or I should provide Optica and our friends a bigger chart later on. This is the design also drawn by myself. This is to tell everybody, if you are interested to co-work with the Taiwan's ecosystem for the photonics PIC ecosystem, you can feel free to come to us, because that we are working from the fabless to foundry to the OSAT, and also to the module level, and also to the end users, such as people will use the silicon photonics chip for their AI server as well. Yes. So Tanya, yes. Next slide, please. So the second slide will be also the last one I want to share with all our friends. This is a little bit of self-introduction that also share with you a good news that we will have International Semiconductor Exposition starting at the beginning of September in Taipei. So I believe many of our friends maybe will come to Taiwan to join the big semiconductor exposition. As well as that Surugashiki, we co-work with all of the major government industry, research industry, such as E3 in Taiwan, and also basically we are a Japanese-based company. So we are working with the Singapore A-Star and also the Japan, even I see the Sumitomo Mizuno-san is also on the line. So we are working with the Sumitomo, with the Fujitsu or NTT or the other Japan's big companies as well. So we host a silicon, we call that is the Heterogeneous Integrated Silicon Photonics Alliance. The short-term form is HISPA. So this, I'm a co-founder and also the vice chairman of this alliance. And, it will be our big honor to work with the Optica, because that this is the, the domestic PIC alliance. We are also, seeking for the opportunity to working with the Optica to try to link the ecosystem. And also whenever you need a business, upstream business from Taiwan, or whenever you need the mass production capacity in Taiwan or in Japan or in the APAC region, that which I'm ESCO right now, you can just feel free to come to us. So because of the time limitation,
YouTube, I would like to let you know that I hereby welcome and accept the opportunity to partner with HISPA. So we will but expect big news between Optica and this heterogeneously integrated silicon photonics alliance. Expect big news with this. This meeting is global, and many things have happened with Asia, as you just heard from Taiwan. I would like to say something else as well. For everyone in the meeting room, and before I give the floor to our final speaker, as you know, we are very active with the CHIPS Act. I know, because many of you have asked me questions over summer, and this our LinkedIn post, that in the beginning of summer, July 9th, we have a notice of intent for the different tools for the packaging of chiplets, and this includes the packaging of photonics. We have some people of NIST in the room. We can also make introductions, but have a look at the website of the Chips for America, and have a look at all the different R&D activities for which they are demanding, they are asking for notice of intent. And notice there is 1.6 billion euro on innovation for these R&D projects. This is for US-based companies, as well as companies who have the possibility of being active in United States. And this is a major opportunity. And one of these companies is the next speaker today. I'm going all the way to both Enschede as well as to Montana. I'm going to welcome PHIX. Thank you very much, Marcel, for being with us today. This is an OSAT. Please let us know what you can do for others, what others can do for you. The floor and the attention of everyone goes to PHIX.
Oh, Jose, I hope you can hear me loud and clear.
Crystal clear.
Yeah, loud and clear. Very good. Hey, thank you so much. I also have some slides, and thank you for giving me the opportunity to present that. So, and check, do you see the slide?
Yes.
Okay, good. Hey, we as PHIX, we are full focused on packaging of all kind of integrated photonic or freeform optic solutions. And we love to do that in large scale. And I will also go to the next page. So we, let's say, are located in the Netherlands, and we have a little bit above 50 people. But also currently we have a US office, PHIX Inc., and also gives us the possibility of supporting, let's say, our US customers also directly from the US. And we also see that we as a company, we have globally a lot of customers in all domains. But also for us, the US market is a very important one. You also see, in my opinion, a nice picture of our new facility. So some months ago, we were able to open our new facility, and that gives us the possibility of growing further. So it has a lot of clean room space, but also a lot of space for the proper equipment to make automatic production possible. And this production activity, we do this for, let's say, all domains which are related to integrated photonics. We see a lot of customers active in LiDAR, in quantum, in biophotonics, in datacom, in sensors, you name it. And we also see them, let's say, for example, maybe an LiDAR application. We see also solutions that in all different, let's say, 35 domains active. Some tried in silicon nitride, some in indium phosphide, you name it. And we package everything on customer requests. And that's also what we are. We are let's say, a service provider, let's say, and we are definitely performing the activity of packaging and everything what is involved in the packaging activity. The photonic PIC itself, there's our opinion, is not a product. So that you need a lot of things to make it functional. So all the optical things need to be connected to a photonic chip. A lot of wire bonding is typically applicable. Thermal management is needed. And at the end of the day, you want to have a module which can be used on a higher level. And that's, let's say, our activity. All things of assembling and coming to a final product. That's what we do. And I have also another example how this could look like. You see a little bit of an animation of a gold box butterfly, some thermal preparation of thermal management. You see here a laser module positioned on a substrate. This is, for example, a silicon nitride chip polished to a certain angle. We also able to flip chip all kind of things on it. We strongly believe in active alignment. And you see by 6 freedom degrees the optimization of this laser module to the silicon nitride chip. And also with the proper epoxies, then they are, let's say, attached, glued together. On the other side, an example of a fiber array could be with a lot of channels, and also with 6 freedom degrees optimize, finding the spot with the low losses, and then it will also be attached. So then we have the entire chain optimized, and hopefully also with low losses, and which then be, let's say, die attached into the package. Some preparation for hermetic sealing, and then the wire bonding, which is, if applicable, will be done. And in this case, also a hermetic sealing. This was an example where, let's say, 2 chips were connected to each other, but we see a massive diversity. Sometimes it is a number of chiplets which needs to be connected. Sometimes a high density of fiber arrays. Sometimes a really high density of electrical wire bonds. We see, of course, also for the quantum applications for low temperatures, for example, on 4 Kelvin, and also all the technology and process knowledge we needed to make applications for 4 Kelvin. That's what we typically do. Our position in the value chain. Some companies, of course, do the development activities. Let's say some companies, of course, let's say they are the front-end foundries of making the wafers. Could be in all kind of formats and technologies. We as a company do all the packaging relating activities, and to a certain degree we do the validation, and then we can ship, let's say, the package assemblies to our customers, which then they use them on a higher level. And one remark I like to make about, let's say, the picture, and that's also our advice of early involvement. We still see that some companies, they come to us at a very late moment and they want to package the thing. And our advice is, if you involve us or during the development, we can help you to bring your design to a good packageable solution. And also for this, we believe we are one of the only companies who also have a packaging design toolkit, which can help you also, let's say, designing your PIC in such a way that at the end of the day is also packageable. And this packaging design kit, you can freely pick it up from our website. So my advice is strongly do that, because it makes, you say, your design easier. It also involves some GDS layers, which also can help you during your process. And at the end of the day, the total cost for your packaging will be lower in higher qualities. This is an example everybody's talking about, let's say, maybe hybrid integration, and this is also a form what we see quite often. You see a high number of chiplets which need to be connected to each other. Some of the chiplets are, let's say, then also directly chip to chip, let's say, connected and optimized for low losses. You see different platforms, silicon nitride, indium phosphide, all the chiplets in their specific area of expertise. But also what is growing by time, of course, the need for high frequencies. So we also have packaging forms up to 64 gigahertz. On the top side, you see also a fiber array. Sometimes you see a density of fiber arrays. That could be in all wavelengths and you name it. So let's say this is also a complexity form which suits us very well. So and the interconnection of a lot of optical components. This, by the way, is a form, of course, of directly interconnect. We see also forms where, let's say, it's more free space optics, where, let's say, you have more, let's say, separate standing components like lenses, isolators, you name it. Also fits us very well. This is my last slide, and give you a little bit of an overview about maybe the diversity of, let's say, packaging solutions we see coming by. We serve customers, let's say, from low volume to the beginning to high volume production. The low volumes also, we have a number of characterization packages. If you have your chip, you comply to a certain set. We also have all the materials for easy packaging your chip, and that you can validate them, let's say, on your bench to a high level. You see maybe also on the top row, the second one from the right is one of the characterization packages. Very easy for your first, let's say, multi-project wafer chips coming off. You see also a number of them where you see maybe from two sides, you see fiber arrays, could be edge coupled, could be, of course, feeder grading couplers. You see sometimes also a very high density of interconnects. Maybe the middle row, the second one on the left, I mean, for example, has 3,300 wire bonds, so very high wire bond densities we definitely see coming by. And yeah, also some other things, let's say like thermal management solutions and other things. You see also some examples if the volumes really go up and we have to produce, let's say, products in higher volumes. We have the equipment, we have the knowledge to do that. So,
thank you so much, Marcel. This is great.
Yes.
And I really would like to congratulate you on the success that you are having with PHIX, the entire team of PHIX. But one question, what can we do to help you?
Now, what of course we let's say would be pleased is also of course solutions of products which come to higher volumes. I think we have a specialty on that, and you see still a lot of let's say solutions they are in the ramping up phase. This is of course also a matter of time and products are really ready of doing that. But we love to serve more customers to higher volumes. So that's one thing we can be helped with.
We have been today discussing many of the technologies. I would like to actually summarize everything with this slide. This slide was shown by Vikas Gupta from GlobalFoundries, and he told us on two sides. On one, we all need to work together to solve still some of the key challenges in a bottom-up approach. On the other hand, we are getting lots of pressure from end users on addressing reliability concerns as well as price concerns. And on the next year, we have a really big opportunity because today you have seen that around us we have companies like, look at the chat, like NASA, like Valeo, looking at us and asking us their demands. We need to work together to offer them those demands. I would like to let you know that these last 2 hours have been a pressure for all of us. So on behalf of Optica, 184 staff, on behalf of our management, on behalf of our board, we are here to serve you. Please share with us your challenges. The technical directors like Dr. Olga Ras, like Dr. Helena Diaz, their job is to understand your technology and find for you ways to show it, showcase it, and connect with potential partners, customers, and talent. If it does not your demand, of course, if you like what we're doing, there's only one thing you can do to support us. If you want us to continue having a job, come for a member of Optica. Thank you so much. Until the next time, Jose Costa and Olga Ras here to serve you. Bye-bye.